Good morning, children. Let's continue. D and F block elements. Have you remembered that yesterday, as we have discussed, related with this one, D and F block elements. Yesterday, as we have discussed about periodic table. Okay, as we said in the periodic table, that how they are going to be placed in between, because these two groups are considered as S block element and these six are considered as a P block element, and in between we are having from group 3 to 12. From group 3 to 12, all these are treated as a D block element. In the case of the D block element, as we said in the previous class, there will be a comparable energy difference between what n minus 1d and ns orbital. That's why both can involved in the bounding. As we said in the previous class, depending upon the last electron enters into which atomic orbital, we can classify it as S block, P block, D block and F block elements. In the case of the this one, the D block element, this series is called as 3D series and this is 4D series and this one is 5D series. Similarly, we are having 6D series. But remember one thing, F block elements are called as inner transition element, whereas the D block elements are called as transition element. D block are called as what? Transition elements. As they are calling it as a transition element because there lies between S block element and P block elements. As this is S block element, alkali metal and alkaline earth metal. P block we are having from group 13 to 18. 13 to 18. As in the first year, you have read about the two groups, remaining four groups you are going to study in future, in second year. So here from group 12 to group 3 to 12, all these are related with the D block element. Have you remembered in the previous class we said D block elements not only important chemically, even biologically also, they are playing very important role. Even they are having some of the characters, all these characters we'll see one by one. Okay. Here we can see that when we are dealing with the D block element, always we can observe that with respect to this one, that is with respect to their characters, when we are moving with respect to the character, as we said that, okay, so here we can say that when we are dealing with their characters, like the D block elements, the D block elements are related with the characters or the properties. Properties we can say with respect to the properties, they are hard and brittle. Okay, they are hard and brittle. They are hard and brittle. That is, I'll write here, they are hard and brittle. They are malleable and ductile. They are what? Malleable and ductile. Malleable and ductile also. Their characters will be malleable and the ductile. They are hard and they are sonorous in nature. When we are dealing with the sonorous character, we can say that metals are showing respective luster also. And another point we can remember that whenever we are dealing with this one, the D block element, these are the they are showing colored character. Most of the D block element ions are colored in nature. They are paramagnetic in nature. Some are diamagnetic also. As we said in the previous class, like zinc, cadmium and the mercury, they are treated as a pseudo transition element. Their characters will be different as with respect to remaining 9 elements of the respective series. And another point we can say that when they have high melting point and high boiling point, even they have the character to form a complex compound because of variable oxidation state, and they are having water, they are electropositive in nature. When you are saying that with respect to the metals, they are electropositive in nature. Nature is electropositive, and even they have a character to form alloys with other. You may be remembering that as we are using usually amalgamate. Amalgam, that is alloys. They are having the character to form alloys. They can form the mixture with other metals. They can form mixture with other metal and they can act as a good catalyst. Okay, good catalyst. And the alloys of mercury, we can call it as water. Alloys of the mercury, we can call it as amalgam. And here all the metals can exist as a solid, exception like the mercury and the gallium. Okay, they are the liquid at room temperature, because when we are saying that with respect to the physical state, and they are showing variable oxidation state, they are having character to form a variable oxidation state. And most of these d block elements, they act as a best catalyst. These are the some general brief characters of D block element. Let us move to the different trends are there. Like the first trend related with atomic size or ionic size. As I said you in previous class, that our topic is dealt with specially with what related with related with 3D series. In the case of the 3D series, if you'll see, it starts from scandium to zinc. From scandium to zinc. Okay, it is going to start from 3D1 to 3D10. It starts from 3D1, but it is end with 3D10. So totally we can say that in the case of the zinc, all the orbitals are filled up, all the electrons are filled up. That's why they are showing different character. Their characters will be different as with respect to other element, other metal atom of the same series, of the same D block element. Here you can observe that when we are dealing with this one, the atomic size, you can see over here, from titanium, vanadium and the chromium, there will be a increase in atomic number. There will be what? Increase in atomic number. But here, slightly decrease from chromium to manganese. And from iron, from manganese to iron, it remains same. It slowly it increases, but there will be no much variation from iron to nickel. And further, it is going to decrease from nickel to copper, copper to zinc. Remember one thing, as we said that to show the different variation, in the case of the D block element can be explained on the basis of important concept. Nuclear charge increases. Okay, we can say that when they're moving across the period, when we are moving across the period, nuclear charge increases. Charge what? Penultimate. Penultimate means earlier to that. That's why whenever we are dealing with such character, okay, whenever we are dealing with such character, always we can remember that with respect to the atomic number, when we are moving So when we are dealing with respect to this one, the electronic configuration, as we said that when we are moving with respect to the across the period, the atomic size, okay, when we are moving across the period, always the atomic size should be decreases. As there is a decrease in atomic number, which indicates that they are showing, because of the variable oxidation state, their characters are going to change. Their characters are going to what, children? They are going to be changed. That's why we said one part over here. This I want to remind that N-1D and NS electron. N-1D and NS electron. That's why whenever we are moving, whenever we are going with respect to the size, whenever we are going to with respect to the size, always from, it will be a decrease in atomic number. Decrease in atomic number, how it is going to be decreases? It is going to be decreases from vanadium, titanium. Okay, always we can remember that when we are deciding when we are deciding the atomic radii, it will be decreases. Further, it can remain constant and increases. This trend is most important. What is the reason for all these variation? The reason can be written either on the basis of the nuclear charge, or even we can write with respect to what? Shielding effect. One by one we'll consider here why there will be a decrease. For a decrease in size, you can write that when there is a decrease in the atomic size, when there is a decrease in the atomic size with respect to from chromium up to chromium, when we are moving from scandium to chromium, there will be a decrease in atomic number. That decrease in atomic number can be justified by increase of nuclear charge. Increase of what? Nuclear charge. Whereas from chromium to copper, they are going to remain almost the same, not exactly same, almost they are going to remain same. But from up to zinc, again there will be an increase. Because when we are dealing with from chromium to copper, remember here, from chromium to copper, the second point we can say that when there is here the electrons n-1d and the ns penultimate and ns both are involved in the bonding. So here we can say that as the electrons are shielding effect of the d electron is small, when the shielding effect of electron, this one d electron is small, nuclear charge is going to be increases. It means that both are going to be cancel out each other. I'll repeat the sentence. The shielding effect of d orbital is so small, nuclear charge increases along the period. Both are going to be cancelled at the midway. At the midway, both are going to be cancelled out. Because of this cancellation, we can say that atomic size is approximately same. There will be no much variation. But from copper to zinc, again it is going to be increases. Because the zinc is having what? 3d10 electronic configuration. What is the electronic configuration of the zinc? 3d10. The electronic configuration of zinc is what? 3d10, where all the electrons are filled up. If they'll ask the separate question with respect to the atomic radii, with respect to the atomic radii, if they are asking the question in exam separately for 2 marks, always we have to write that how does the atomic radii are going to be vary. Okay, as we will write, because always in the inorganic this one section we are having exceptional cases. That's why when we are defining with respect to the this one, the atomic radii, you can say that it will be decreased from scandium to chromium, it remains same over here, and further increases to zinc. Decrease because of increase of nuclear charge. This chromium to copper, shielding effect and nuclear charge are going to be cancel out with each other. When they are going to be cancel out over each other, the atomic size remains constant. Then from copper to zinc, there will be a slight electronic configuration. The electronic configuration is what? Electronic configuration will remain electronic configuration will remain zinc. That's a 3 important point we need to write for 2 marks. For 2 marks, all these 3 points we need to explain in a systematic manner. In a systematic manner. And another point we need to remember that instead of atomic radii, if we are going with respect to ionic radii, in case of an atom, here question comes with respect to what? Oxidation state. Point arises because of what? Oxidation state. Question arises that when there is a atomic radii or ionic radii, question arises with respect to what? With respect to the oxidation state. And another point we can say that then the ionic radii decreases with the increase of oxidation state. Let me repeat the sentence. Ionic radii decreases with the increase of oxidation state. Oxidation state. So how you are going to write? Oxidation state and ionic radii are inversely proportional. Both are what? Inversely proportional to each other. When they are inversely proportional to each other, we can write the sentence that because oxidation state increases. So here we can say that always the oxidation state are going to be increases in the case of oxidation. In the case of oxidation, and that species will act as a reducing agent. Similar concept you can write with respect to this one, that is ionic radii. Therefore, you can write one sentence over here that in the case of the ionic radii, in the case of the ionic radii, we are going to write what? With respect to what? Okay. We are going to write with respect to what? Oxidation state. And another point we can remember that this neutralizes the effect, because when we are dealing with, for example, the first transition element, if we are taking with respect to the scandium will show +3 oxidation state. Whereas if you'll go for the scandium will show +3 oxidation state. Because what I said in the previous class, variable oxidation state. Oxidation state can be expressed in terms of water. When we are dealing with the oxidation state, always you should see that it should be in the water sum of number of electron present in, sum of the number of electrons present in n-1d and ns electron. That's why when the scandium is present in +3 oxidation state, or we can take the titanium present in +2 or the titanium present in +3. Higher is the oxidation state, smaller will be the size. And the question arises that whenever we are having the transition metals, this size will be smaller as compared to the main group element. Main group element is nothing but what? Related with S block element and the P block element. This is the point related with what? Either atomic radii or ionic radii. When question arises for the atomic radii and ionic radii, same point you can write with respect to what, children? Ionization enthalpy. For example, if we are writing with respect to ionization enthalpy, we can write with respect to ionization enthalpy. When we are writing with respect to the ionization enthalpy, what we said that the amount of energy needed to remove valence electron. Ionization enthalpy corresponding for what? Ionization enthalpy will be corresponding for delta Hi. Ionization enthalpy, the amount of energy needed to remove valence electron. Or we can say that loosely held electron. Or we can say that with respect to what, children? Loosely held electron. That's why the first ionization enthalpy of D block element. Because when we said that with respect to what? The number of the electron lost by, because earlier we said, in earlier slide we said that as they are going to show different oxidation state or variable oxidation state. Variable oxidation state. That's why whenever we are dealing with the first ionization enthalpy of D block elements, first ionization enthalpy of D block elements, okay? Because we are going to compare D block with the earlier block as S block and as well as P block. This will be higher as compared to with respect to S block elements. This is the important point we need to remember, that with respect to the S block element, the D block elements are having higher, but these are less than P block elements. These are less than what? P block elements. That's why whenever we are dealing with respect to the D block, always, because D block element are treated as what? A transition element. Transition element. Name itself indicates that transition element lies between S and P. When they lies between S and P, their characters also lies between S and P block elements. S and P block elements. That's why with respect to the ionization enthalpy, another point we can say that with respect to scandium, if we are going with respect to the scandium will show scandium will show the ionization enthalpy of about 631, okay? 631 kilojoule per mole. 631 kilojoule per mole. Whereas, as we said that across the period up to chromium, we are going to get what a same atomic size. Remember here, size and ionization enthalpy are inversely proportional. Size and ionization enthalpy are always inversely proportional. That's why with respect to size and ionization enthalpy, this will be the simplest way to understand with respect to D block element. That's why with respect to scandium, it will be 631. Then we are having the titanium about 661, titanium of about 661. Scandium, titanium, vanadium of about 681. That means that as the atomic size decreases, ionization enthalpy is going to be increases. That's why I said to remember this one, size, atomic size and ionization enthalpy are inversely proportional to each other. What they are? They are inversely proportional to each other. And another point, as we said, that they are with respect to this one, then when they are decreasing up to chromium and they are going to remain same up to copper. That's why from manganese to with respect to copper, there will be no much variation in ionization enthalpy. Why there will be no much variation in the ionization enthalpy? Because atomic size is going to remain constant. When atomic size is going to remain constant, there will be no much variation in ionization enthalpy, whereas zinc will show higher. Zinc is showing around 908 first ionization enthalpy, highest for zinc, because as we said that because of the D10 electronic configuration, because of the 3D10 electronic configuration, because of the completely filled electronic configuration, 4s2 3D10, zinc will show highest ionization enthalpy. This is the another character. Two properties, two characters we have completed, one with respect to atomic size and ionic size, and the second is related with ionization enthalpy. Size and ionization enthalpy are inversely proportional. That's why both the properties I have taken together. That's why whenever we are dealing with such point, always you can remember that whenever we are dealing with such point, what I said that always we have to consider with respect to this point. This is the most important relation. Most important relation. And another point, as we said that these are what they are having okay, these are having metallic character. Based upon the, when we are saying that metallic character, their melting point should be high. As we said that they are metallic in nature. Their characters are what? Metallic. They are the malleable and ductile, we said. They are what? Malleable and ductile. They are malleable and ductile, and they are having high melting point. If you'll observe this graph, you can see that melting point is going to be increased from titanium to chromium. Further, because we need not to remember the parameter, we need to remember the variation from where they are going to be increases, from where they are going to be decreases. Okay, then you can observe the graph over here that from titanium to chromium there will be an increase, and when they are going, because there will be exceptional case, because what we said that amongst all the D block element, mercury is the metal which is exist in liquid state. Mercury and gallium, even gallium also, they are going to exist liquid at room temperature. And these are remaining are the solid, and they are having high metallic character. That's why you observe the graph over here. From titanium to chromium, there will be an increase in melting point. When there will be an increase in this one, the melting point, this can be explained on the basis of what? Relatively low ionization enthalpy. We can say that when there will be increase in the melting point, it corresponding for what? Low ionization enthalpy. Because of the low ionization enthalpy, the melting point are going to be increases. Or we can say that another point that, and one more thing we can say that there will be a vacant d orbital also will decide metallic character. Vacant d orbital also will decide character. Vacant d orbital, because those vacant d orbitals are responsible to show the metallic character. That's why the most important, the metallic character of the transition metal is doing to water. It is due to relatively low ionization enthalpy and the number of metal vacant orbital. When there will be a low ionization enthalpy of the vacant d orbital, then they are going to show what? There will be a increase in what? A melting point. Further, from chromium to manganese decreases and slowly it is going to increase to iron. That's why when there will be increase in this one, we can write that the strength of the strength of bonding, the strength of bonding always related with what? A number of unpaired electrons. Have you observed that many of the characters in the d block element are related with the number of unpaired electron? Unpaired electron will decide the character. Unpaired electron, because more are the number of unpaired electron, what we can say, more will be the metallic character, or they will be having high melting point. That's why when we'll go for this one, the number of unpaired electron, you can see over here how the number of unpaired electrons are going to be present over here. Here in the case of the scandium 3+, we said that number of unpaired electrons are 0. Number of unpaired electrons are 0. Whereas in the case of the 3D 3+, we are having number of unpaired electron as 1. 3D 1, number of unpaired electron in the titanium 2+ as 2. That means that number of the unpaired electrons will decide metallic character. Even they can decide what? With respect to melting point also. With respect to melting point. That's why whenever they are deciding that metals are electropositive in nature, and in the case of the d block element, what I said, most of them are metallic. We can say that most of them, we cannot say 99% they are metallic in nature, and they are high melting point and high boiling point. They exist as a solid except mercury and gallium. This also we need to remember, except mercury and gallium. The melting point can be decided on the basis of the strength of bonding is roughly related with the number of unpaired electron. Because strength is more, then only they can show with respect to what? The strong bonding. When they are showing the strong bonding, that time only we can say that we can say that they are having what? A high metallic character. Okay, listen here. That's why I said the high melting point of these metals are attributed to the what? Involvement of greater number of electrons from n-1d in addition to ns, because n-1d will be there along with ns. This will be responsible to show the metallic character along with this one. That's why one line we can remember here, the high melting point of these metals. Which metals? Transition metals. Transition metal attributed to what? Involvement of greater number of electrons from n-1d. As we said in the case of the scandium 3+, d will be 0, 3d 0. 3d 0. Whereas if we are going with respect to the titanium, if we are going with respect to the titanium plus 2, it will be 3d 1. Like that, number of unpaired electrons are increases. We said here that due to the addition of the ns electron in the interatomic metallic bonding. So number of unpaired electron will be directly proportional to bonding. N will be directly proportional to what? Bonding. Now, more are the number of unpaired electrons, strong will be bonding. And another point we have continued over here. If any row, the melting point of these metal rise to maximum at D5, okay, except anomalous values of manganese and technetium, they fall regularly as the atomic number increases. Yes, because yesterday while writing the electronic configuration, as I said, especially in chromium and copper, half-filled and completely filled d orbitals are more stable. The same concept they have said over here, where that ionization enthalpy also depends upon what? Stability. Ionization enthalpy also depends upon what? Stability. With respect to stability also we can decide. With respect to number of electrons also we can decide. Okay, that's why we'll come back to this one, the graph we said over here. Observe the graph over here. Once again, from titanium to chromium increases melting point, then it is going to be decrease, further remains same over here. From iron to nickel, and further it will be up to copper. So like this, the variation can be observed. And this variation we can write on the basis of what? On the basis of number of electrons. Number of electrons. The next point related with what? Enthalpy of atomization. We said that enthalpy of atomization. When they are saying with respect to the enthalpy of atomization, we are going to consider only with respect to what? 3D series. And this green line will be corresponding for 3D series. This will be the first series of transition element. This will be corresponding for 3D series. And this blue line corresponding for 4D series. And this red line considered for 5D series. There will be a 3 series in the transition element. 3D, 4D and 5D series. When we are dealing with enthalpy of atomization, okay, when we are dealing with the enthalpy of atomization, always we are going to write that the shielding effect of electron is not that effective, because we know very well that D will show less as compared to S. Now, hence the net electrostatic attraction between nuclear charge and outermost electron increases, and there will be a decrease in ionic radius. That's why whenever we are dealing with such graphical representation, always need to concentrate that how they are going to remain constant and in what way there will be a slight increase and further it remains increases. That should be a remarkable difference. Slight difference, slight variation will be there. That graph, this graph is necessary to remember with respect to only 3D series, as we are going to consider from scandium to zinc. Scandium to zinc is most important for us. We are not at all dealing with what? Second series or the third series. We are going to concentrate only on the first series of transition element. Okay. Here one more point we said. Shielding effect of the d electron is not that effective. Not that effective is nothing but what? It will be less. We are going to consider it as a less. But when it comes to the question related with F block element, have you remembered that in the introductory part, as I said, when we are moving down the group, atomic size increases. And atomic size increases can be explained in terms of what? Principal quantum number, because number of shells are going to be increases. Principal quantum number increases. With the increase of principal quantum number, the n value increases. As the n value increases, atomic size are going to be increases down the group. The same point they have read over here. The filling of 4f orbitals, 4f before 5d orbital result in a decrease, because when we are deciding this one 4f before 5d, this time we can apply n plus l rule. Based upon n plus l rule, while filling the electronic configuration, as we know that to decide Always in the lower is the value of n plus L, lower will be the energy, or lower will be the energy content, and always the electrons are filled up in the increasing order of energy level. And that reason is called as lanthanoid contraction, which is essentially compensate for the expected increase in atomic size with the increasing atomic number. The same point as we have read in the periodic properties, same concept can be written for this also. Because in the periodic properties, we said with respect to general, not with respect to S block, P block, D block, or F block. But here in this case, we are going to deal only with the 3D series. Another point we said that the net result of the lanthanoid contraction is that the second and the third D series, expected same atomic radii like the zirconium and hafnium. And this point we can call it as lanthanoid contraction. The specific word we'll use as a lanthanoid contraction. As a lanthanoid contraction. And when we are dealing with the lanthanoid contraction, even we said with respect to this one, another one point we said, greater the number of valence electron. As I said that n number. For the scandium, it will be 0, whereas the titanium will show 3D1. Scandium 3D0, scandium 3 plus, scandium atomic number 21. 21 minus 3 will become electronic configuration of argon. So here 3D will be 0. Scandium titanium 2 plus, titanium electronic configuration is 22. That's why we can write it as the number of unpaired electron. Number of unpaired electron increases, stronger is the resultant bonding. When stronger is the bonding, enthalpy of atomization is an important factor in determining the standard electrode potential. Have you remembered the galvanic cell, children? That E naught of zinc will be minus 0.76 volt. Minus 0.76 volt, whereas the E naught of copper, we have taken it as plus 0.34 volt. Better to remember this concept with respect to any of the example. It will be convenient for you to write in the exam. Okay, while writing in the exam, this is most important. Another point we said that when metals are with very high ionization enthalpy of atomization, that will also corresponding for very high boiling point, tend to their noble reactions. What tend to be their noble reaction? It indicates that when they are having high atomization enthalpy, the amount of energy needed, okay, we are going to take with respect to the amount of energy needed to remove the valence electron, we said. Higher is the oxidation state, smaller will be the size, and even we can consider size with respect to ionization enthalpy. So 3 points we can correlate over here. With respect to those 3 points, even we can define the next, this one, the point related with electrode potential. In the case of the electrode potential, what I said earlier, that in the earlier, this one, what I said, with respect to the, since the ionization enthalpy is an important factor determining the standard electrode potential of a metal. Metals with high ionization enthalpy of atomization. D block elements are best metal, best catalyst, malleable, ductile, lustrous. These are the some of the characters. They are having catalytic behavior, variable oxidation state. One of the plus point related with the D block is variable oxidation state. In the case of the electrode potential, we are going to explain with respect to only 3D series. Only with respect to 3D series. So with respect to the electrode potential, we can say that the number of the electrons which are going to be, because change in the oxidation state. As I said that with respect to the oxidation state also we can atomic size or ionic size. We can explain with respect to their atomic size and ionic size. Okay, if we'll see over here, the standard electrode potential -2 -1.5. Here we have come to 0. That is SHE. 0 corresponding for what? Hydrogen. Hydrogen. You can see over here from titanium, vanadium. Okay, titanium, vanadium, and the chromium. You can observe over here copper is at the positive level. At the positive. And when copper acts showing the oxidation state at positive, it acts as a cathode. It acts as a what? Cathode. And the negative SRP value, they behaves as a anode. They behaves as what? Anode. They behaves as anode. Negative R behaves as a anode and the positive R behaves as a cathode. And when we are writing with respect to the electronic configuration, as we said that here electronic this one, the standard enthalpy of this one ionization enthalpy can be correlated with enthalpy of atomization. So here they can observe over here titanium. Titanium is what? A negative, whereas vanadium, then we are having chromium, manganese, iron, cobalt, because we are going to show slight variation over here. They can show two oxidation state, they are going to show two SRP values. And further copper is showing plus 0.34 volt. Hydrogen is 0. Hydrogen is 0. And plus 0.34. Beyond the 0, we are going to take it as a positive. We are going to take it as what? A positive. That's why whenever you are going to decide with respect to electrode potential, with respect to electrode potential. Another point, as I said, that D block element shows magnetic. They are paramagnetic in nature, diamagnetic also, ferromagnetic also, depending upon again the same point number of unpaired electron. Same table we have taken as it is in NCERT book. Unpaired electrons, because mu is equal to square root of n into n plus 2. Magnetic moment can be calculated by using the formula square root of n into n plus 2. N into n plus 2. N represent number of unpaired electrons. Therefore, when the number of unpaired electrons are 0, mu will become equal to 0. Then when the mu is 0, these are diamagnetic in nature. They are diamagnetic in nature. Whereas when this is 1.73, this is what? With respect to 2.84, we are going to substitute over here. If the number of unpaired electrons are 1, 1 into 1 plus 2 is equal to square root of 3. Square root of 3 is what? 1.73 Bohr magneton. Bohr magneton. Same way you can calculate with respect to 2, 3, 4, 5, 6. Then we are having with respect to what? 3d7. 3d7 with respect to cobalt 2 plus. Okay. Then D contain 5 suborbitals. All are paired except 3. Here 2, 1 and 0. One more point I want to show with respect to zinc, that zinc is diamagnetic in nature. Already we said in the introductory part that zinc shows different character as compared to remaining 9 elements. As with respect to remaining 9 elements, zinc shows different character. Zinc shows different behavior. Okay, here one of the behavior we can say that earlier we said with respect to atomic size and ionic size. Another point we can write with respect to ionization enthalpy also we said. Highest ionization enthalpy for zinc around 908. Whereas if you'll see the number of unpaired electron for the zinc, electronic configuration will be 3d10. All these are decided on the basis of what? On the basis of electronic configuration only. Electronic configuration only. You can observe over here cobalt, nickel and iron. They act as ferromagnetic material. Ferromagnetic material. Ferromagnetic material means what? In absence of magnetic field also, they are going to show deflection. And slight deflection is exhibited by paramagnetic substances. Paramagnetic substances. That's why whenever we are going to write with respect to number of unpaired electron, more are the number of unpaired electron, more will be magnetic behavior, because mu is directly proportional to n. Mu is equal to what? Square root of n into n plus 2. More are the number of unpaired electron, more will be magnetic behavior. And when they are containing number of unpaired electron, these are paramagnetic in nature. Paramagnetic means the material which shows slight deflection in magnetic field. When they are showing slight deflection in magnetic field, they behave as paramagnetic substances. Whereas in absence of magnetic field also, if they are showing deflection, those are ferromagnetic material. Those are what? Ferromagnetic material. And here the ferromagnetic material are like iron, cobalt and the nickel. Iron, cobalt and the nickel. And the remaining properties and all we will continue in the next class, children. Some of the properties lies as, still we will continue with the magnetic property, catalytic behavior, and why they are involving in what? Complex formation, colored nature. All these are the some of the important characters are there. With respect to n only we are deciding their color. This n, this point is very, very important. This point is very, very important, because n only will decide many of the characters. It decide metallic character, it decide oxidation state, it decide enthalpy of atomization, it decide magnetic behavior, colored character, even variable oxidation state. Many of the things are there which can be decided on the basis of n. Okay, all these remaining points will continue in the next class, children. We'll wind up over here. Thank you, one and all.